If you work in a lab, you know this pain. You spend weeks, maybe even months, building this absolutely beautiful assay. It works perfectly on your bench, and then you hand it off, and it just completely falls apart. In this explainer, we're going to unpack exactly why this happens so often, and more importantly, how to build methods that are actually built to travel. Oh man, you know this exact feeling, right? Your calibration curve was perfect, your controls were tight, everything just looked clean. So you write up the SOP, you hand it off to the next lab, and then you get the call. The signals are all over the place, the CVs are through the roof. It is honestly one of the most frustrating and expensive problems in our industry. So what is going on here? This isn't just a fluke. This kind of failure happens all the time when a method moves from a development lab to a QC lab, or from a sponsor to a CRO. It kicks off this mystery that can cost weeks of troubleshooting, it blows up project timelines, and frankly, it just destroys the trust between teams. That really is the million-dollar question, isn't it? The receiving lab swears they're following your SOP to the letter, but the results just aren't there. So you start to wonder, is it their pipetting technique? Is their plate reader different? What critical piece of the puzzle is missing here? Okay, so let's play detective for a minute and investigate the scene of the crime. When an assay fails on transfer, the blame game almost always starts. Everyone's pointing fingers, looking for that one single thing that went wrong. But the truth? Well, the truth is usually a lot more complicated. These right here are the usual suspects. A different brand of plate reader, a new lot of antibody, maybe a tiny difference in how an operator mixes a plate, or even just the humidity in the new lab. Any one of these things can absolutely derail a fragile assay. But the real question is, are they the root cause? And here it is. This is the absolute key insight. The problem isn't the person or the equipment in the receiving lab. The failure was actually baked into the method from the very beginning. The method itself was fragile. It was only ever optimized for one specific lab and one lab only. So how in the world do we end up creating these brittle, fragile methods? Well, it almost always comes down to a really common, really intuitive, but ultimately flawed way of doing things. We fall into the one factor at a time trap, or as you'll hear it called, OFAT. Now the logic here seems totally sound, right? It feels very scientific. You know the drill. Hold everything else steady, change one thing, like your antibody concentration, find that perfect sweet spot, lock it in, and then move on to the next variable, like incubation time. It feels traceable, it's simple, but it is dangerously incomplete. I love this analogy because it just hits the nail on the head. OFAT helps you find a single perfect point under one very specific set of conditions, but it gives you zero information about the landscape around that point. The chair is perfectly stable right where you built it, but the second the ground shifts, which it always does in a transfer, the whole thing just falls over. You see, OFAT has a blind spot. It cannot see how variables interact with each other. For example, what happens when your antibody concentration is a little high and the lab temperature is a little warm? Does the whole assay just collapse? OFAT has no idea because it never tests those things together. It creates a rigid recipe for a world that is anything but rigid. Okay, so if OFAT is the villain in our story, who's the hero? Well, it's a completely different way of thinking called design of experiments, or DOE. This is how you build methods that aren't just optimized for one perfect day, but are genuinely robust enough for the real world. So unlike OFAT, which changes just one thing at a time, DOE is all about changing multiple things at once in a really smart, structured way. This lets you see not just the effect of each individual variable, but crucially, how they influence each other. It's about mapping the entire terrain, not just climbing a single sharp peak. And the process is so powerful. First, you screen a whole bunch of variables to figure out which ones actually matter, the critical few. Then you optimize by mapping out a wide, stable operating window. Think of it like finding a flat plateau, not a pointy mountaintop. And finally, you validate by deliberately simulating the transfer before the assay ever leaves your lab. And this is the fundamental shift. With DOE, you're not just handing the next lab a simple recipe and wishing them good luck. You're giving them an engineering document. It tells them which parameters are critical, which ones have flexibility, and what the true validated operating ranges are. It's basically a map to help them navigate their new environment. All right, enough theory. Let's put this to the test. Let's look at how these two very different approaches actually play out in the real world, side by side. This is where the rubber really meets the road. So, on one side, we have transfer A, which was developed using that traditional OFAT method. And on the other, we have transfer B, developed using DOE. Now, on paper, in the development lab, both methods were considered optimized. But what happened next? Well, that's where their stories diverge, big time. I mean, just look at this data. It tells the entire story. First off, the DOE method was actually 2 weeks faster to develop in the first place. But the really jaw-dropping difference is what happens next. The OFAT method fails right out of the gate, which kicks off 3 weeks of troubleshooting. It took over a month to finally get accepted. And the DOE method? It passed on the very first try and was accepted in less than a week. The total impact here is just staggering. That one initial failure from the OFAT method added over 5 weeks of delays to the project timeline. That upfront investment in DOE Tomly didn't just prevent a failure, it actually made the entire process faster from start to finish. Okay, so let's bring this all home. What's the big lesson we can take away from all this? Where does the responsibility for a successful, painless transfer actually lie? Ultimately, this is what it boils down to. We have got to stop thinking of transfer failures as a QC problem or an issue with the receiving lab. They are a direct consequence of how the method was built in the first place. A fragile method was thrown over the wall, and honestly, its failure was almost guaranteed. So before your next tech transfer, this is the question you need to ask yourself and your team. Have you just found one perfect spot where the assay works on your bench? Or have you actually stress tested it and built a method that is truly prepared for the real world? Now, obviously, this is a huge topic, and every single assay has its own unique quirks and challenges. So if you're wrestling with a transfer right now, or you have questions about how these ideas might apply to your own work, I genuinely want to hear about it. Drop your questions and your stories down in the comment section below. And finally, if this explainer helped shed some light on this frustrating problem for you, do me a favor and hit that like button. It really does help other people find it. Make sure you subscribe for more deep dives into complex topics just like this one. And if you know a scientist who is stuck in that endless troubleshooting loop, please share this with them. Thanks for watching.